I'm going to find the volume of an object of revolution that's determined by this shaded area. The shaded area is bounded by these three lines. I'm going to rotate it around the y-axis, and then I'm going to do something weird. I'm going to calculate the volume, but not the easier way to do it. The natural, easy way to do this with an integral would be to use the disk method, where you slice this up into slabs to get an approximation, and then take the limit as the width of those goes to 0. I'm going to do it with the shell method, which is a little bit different and more complicated in this particular example, but sometimes it's more useful than the disk method. If I grab one of these cylindrical shells, just a random one, it will look like this. Something like that. So what's happening is I'm starting from the center and I'm building these shells and then working my way out. The initial shells that I start with around the center are going from this line all the way up to 10. So they're really skinny and they're really tall. And then as I move out, they're getting more wide and they're getting shorter. And then finally, as I get way out here, they'll be really short and really wide. The width of these things is a small width in the x direction. I'm going to call it delta x, because if I take more and more of these shells from my approximations, then they get smaller and smaller in terms of the width delta x. And I want to let that width shrink down to 0 so that I can calculate the exact volume with an integral. So my approximation of the volume before I take the limit, I get by adding up the volumes of these shells. So I need to calculate the volume of each shell and then add them up. To get the volume of the shell, I'm going to think of this thing as, well, I'm going to split it open. It looks kind of like a toilet paper roll. I'm going to slice it, split it open, and unroll it. And when you do that, you get this long rectangular object whose height goes from this line 2x all the way up to 10. So to get that height, take the top y value minus the bottom y value. The top y value is 10, and then this bottom y value is 2x. It depends on which x value you're picking down here. So I think probably the hardest part of this, doing this with the shell method, is that you have to understand how to get the height. No matter which shell you're looking at, you pick an x value, and to get the height of the shell, you're going to go from 10 down to the line 2x. The line, the y value of 2x is the distance from here to here. I want to subtract that distance from the distance from here to here, which is 10. All right, this little width is delta x, and then the long length is the circumference that I get after I've cut that and unfolded it. So when you unfold this thing, your circumference is pi times diameter, or 2 pi r, where that radius is your x value. I don't know what color to use. It's going to be hard to see no matter what color I pick, but the radius of this thing is the x value. So you have some y value here, the corresponding x value on the line y equals 2x is what's determining that radius. So this is 2 pi x. that means my approximation is just length times width times height. I'm going to write it in the order 2 pi x times 10 minus 2x times delta x. This is a Riemann sum. It's a function times delta x. When I take the limit as that delta x, that length element shrinks down to 0, I get the exact volume, which turns into an integral. And I will go ahead and multiply this x into the parentheses. My x values are running from 0 out to 5. So if I focus my x values going that way, it will automatically pick up what's on the left side as well. All right, now I just need to take the antiderivative, plug in the bounds. So I'll run through that real quick. I'm using the power rule. All right, and now what I get, I plug in 5 first, then I do minus, I plug in 0. When I plug in 0, both terms 0 out, so I just need to plug in 5. 5 times 25 is 125. And again, this is 125, but it's times 2/3, so I'll write it as 250 over 3. And then this 125 in terms of thirds is 375 over 3. So this is 2 pi times, I'm going to get 125 over 3. So if I multiply that out, I can rewrite it a little more nicely as 250 pi over 3. That would be the volume of this cone, calculated the more challenging way, but a way that is helpful to know for other situations, not like this one.